Okay, so today I'm just going to talk a few more things about inequalities, yeah, with some additional examples, and then we will look at two important theorems. They are called the Borel-Cantelli lemmas, right? Okay, so let's see. First, maybe I want to say something about just to refresh something about distribution of maximum and minimum of random variables, okay? So for example, you may have x1, x2, xn are dependent and identically distributed. So usually this is denoted as IID, yeah? Random variables, okay? With, of course, they have to have finite mean and variance. All right, otherwise, some of the moments don't exist, yeah? Okay, then we want to find, okay, so we want to find the distribution of max, okay? So maximum means among these random variables, right? So they will turn up a particular number. So you want to find the largest one, right? Okay, so for example, if you do an experiment, if you do an experiment, right? So maybe you have some distribution. You take your values x1, x2, and so on, right? Okay, then you'll find the largest among them, right? So in this case, the largest among them is this one. And then you repeat this experiment. So the next time you do it, you may actually get something like this. Your largest one may be somewhere here. So you collect this value, you collect this value. So then you plot these values, yeah? So you repeat this many times and you take the largest values, okay? Then you can have a distribution. Okay, so the max of x1 until xn is still a random variable and it has a distribution. Okay, so you probably maybe you have already learned it in year 2, right? But just to refresh, yeah. So you use the CDF method. Okay, so this is the CDF. So this is equal to max less than or equals to y, right? So, okay. So now you have to think a little bit about what it means when you say the maximum of x1, x2 until xn is bounded by y. This is equivalent to saying that all your x1s, x2s are, all of them are bounded by y. Okay, and this one you can decompose it into a product because you have the assumption of ID, right? Okay, so let's go back to this part. Okay, now when you say the largest among x1, x2 until xn is bounded by y, it is equivalent to saying this statement, yeah, because you think about it, if in your whole class, right, if you know that the person who got the highest mark, all right, does not exceed 65, then that statement is the same as saying everyone got marks that are less than 65, right? Okay, if I tell you that the highest score in the class, right, is 65, it means that everyone got marks that's 65 or less. Okay, that's for sure, yeah. Okay, so that's why this part is equivalent, yeah. So once you have this result here, you can see IID, so you can take the product, and because they are identical, so basically you can take one of them, right? You can maybe take x1, and the rest are identical, so it just becomes power of n. So therefore, your density, right, Fyn will be you take the derivative, right, n, okay, d y of this, okay, and then p xi, so x1, so n minus 1, okay. All right, okay. So you basically have this result here, the general result, okay. So let's look at some examples when the distribution is given. Okay, let's say suppose x1 until xn, they are uniformly distributed between 0 and 1. So I want to find, so I'm interested in the max. So I would have this. Okay, and as a result, okay, right. Now this one is simple because this probability is basically just okay, by geometry this is just y, right? So y power of n. Therefore, your f of y is you differentiate this CDF, right? So you get n y n minus 1. All right. Okay. So in this case, your y is running between 0 and 1. Right? Because your max can go between 0 and 1, yeah? All right. You can check that this is indeed PDF, right? Because you check, right? So this is basically just, all right. Okay. So once you know this, then I can find something like the expectation of the max. So this is basically just expectation of yn, and that's very simple. So I'll just take y minus n, this, okay, dy 0, 1. So this becomes n y n plus 1 over n plus 1, 0, 1. So I get n over n plus 1, okay? Right, so the expectation is n over n plus 1. And you can also find the variance, right? So you find the second moment, y square and y. So this will be n y n plus 2 over n plus 2, 0, 1. So it's n over n plus 2. So your variance of yn is the second moment minus the square of the first moment, right? So you can have let me see, you will have n plus n plus 2. So Okay, so you can do the algebra and simplify it. All right. All right. So the distribution of max is doable. Okay. But sometimes, so you may want to just know something about the expectation of the max, right? And of course, you can do this by evaluation if you can do this part, yeah. But sometimes this may be difficult, right? And if you want to make some progress on knowing the expectation, then you can actually use your Jensen's inequality. So I'll show you an example later, right? So this is the distribution of maximum. You can also have distribution of minimum. So let's see. So again, same example. I use uniform. So suppose my Wn is the minimum of x1, x2 until xn, right? The smaller one. Okay, the minimum. So now for minimum, instead of starting with the CDF, we start with the complementary CDF. So we ask ourselves, the complementary CDF is defined as the following. Now, what is the reason for doing so? The reason is so that you can write the equivalent statement like this. Right? Now, look at this carefully. When you say the minimum among them is at least W, it means that all of them, right, are at least W, okay? Is equivalently saying that, okay, an analog is the following. If I tell you that the lowest class, the lowest score in the class, right, is 70. That means everyone's score is at least 70, right? Correct? If the lowest score in the class is 70, then I know that everyone must get at least 70. Okay? So you have to be careful with the minimum, and you can't start with the CDF, because in this case you will end up with this thing, and you can't make any clear statement about this. If you say the minimum, right, is at most W, then there's no joint statement that you can say like this. You think about it, right? If you say that, okay, the minimum is not exceeding certain score, then there are many possibilities. All right, so instead of working with the CDF, we work with the inverse, the complementary CDF when we are talking about the minimum, right? So again, here by ID property, you can get this. All right, and therefore your CDF, right, is just the complement of, okay, this part, okay, so 1 minus that, so therefore your PDF is the derivative, and you will get so again, so this one will be 1 minus, so you can further write it as a distribution function. Okay, so your FW will be, you take the derivative of this thing, so you get N 1 minus P x1 N minus 1, and then you multiply with the derivative here, right? So as you can see, when you take derivative of this, there's a negative, right? Okay, so you take derivative of this inside term here, so you will get also a negative, and then you will get d over d w p of this, okay? And this negative and negative will actually cancel. All right, so you end up with this result. So although this is a general formula, I do not encourage you to memorize it. You should not memorize this formula. All right, this is just to tell you at the end of this sequence of reasoning, you get this result. All right. What you should master is this understanding. Once you have this understanding and you know that you can find your probability density function by differentiating the distribution function, you are fine already, right? Okay, you don't memorize this thing, yeah. This one is just working out the results only. Okay, in a general form. The important understanding is this part. Okay. All right. Okay. So this is the general result. Now I will just maybe show you what you get when you have a uniform distribution, right? Okay, so you work out this, you will get this thing, yeah, which is E1 minus P of X1 over, okay. Okay, so basically this is just 1 minus W power of N, right? Because again, this is uniform, 0, 1, so less than W, so it's this rectangle, right? So it's so this probability is W, right? So 1 minus W, and therefore your f of your distribution function is 1 minus W power of N, and your PDF is you take this derivative, so you get N 1 minus W N power of 1 W, okay? And your W is between 0 and 1. All right, okay. So basically you have this one, and if you notice, right, this is actually a beta distribution, right? This is the PDF of a beta distribution where your alpha is equal to 2 and your beta is equal to n. If you recall the beta distribution, it has this form, yeah. T alpha minus 1, 1 minus T beta minus 1 over the beta function. Okay, the beta function is defined as the following gamma function. Okay, it's defined as a gamma function. So in this case, you basically have gamma of 2, gamma of n over gamma of n plus n plus 2. Okay, let me see. Is this? Oh, sorry. No. Sorry. There's none. Okay, there's no W here because yeah, there's no W here. Right? You differentiate inside you just get -1. Okay, sorry. So there's no W here. So it's still a beta, but it's with alpha equals to 1. Okay. So 1 minus 1, so you get t to the power of 0. So this will be 1. This will be n plus 1. Okay. So gamma of 1 is 1. So your gamma function of an integer is the factorial, all right? So this will be n factorial. So this will be n minus 1 factorial. So you cancel off, you get 1 over n here. So you take reciprocal, so you get the n here. Okay? Right? So we know that if your x are uniform 0, 1, then its minimum has a beta distribution, okay, with these parameters. All right. Okay, that's just to refresh your mathematical statistics results. Okay. Okay. So now I want to show you how to use Jensen's inequality to get a bound for expectation of the max. Okay. Okay. Suppose x1, x2, xn IID random variables. With finite mean and variance sigma squared, right? Such that expectation of the moment generating function is bounded by the following. Okay. Then this is bounded by the following results. Okay. So how to show this, right? So by Jensen's, so we start with Jensen's inequality. Okay. Now you are looking at Jensen's inequality, so you have the following: E of t of this is less than or equals to this thing. Okay. Remember Jensen's inequality. You have what do you have for Jensen's inequality? So your exponential function is convex, right? Just to remind you, Jensen's inequality for convex functions. So you have okay, right. So basically, if you take your exponential function here, the exponential function is convex, yeah? Okay, your exponential function is going up like this, so any 2 points, yeah? Any 2 points, the point on the line will dominate the point on the curve, yeah? Okay, so exponential function is convex, so you apply this function, okay? So you get this inequality, okay? All right, so is it clear? Okay, so this is your function, yeah? Your function is so you treat this max of all this as one random variable, right? So your function is the exponential function. Okay. All right. Now, this guy here is the same as the following. Okay. Because the reason is because your max is applying on this random variable, right? So it is the same as applying it on the constants, right? Because E of t of max of this, if let's say your x3 is the largest, right? Is max, then you will get E of t x3, if, for example. So over here is the same, right? If you write it like this, right? If your x3 is the max, then from here it will take out E of t x3. Okay, so these two ways of writing is equivalent. All right, and then I further claim that this is bounded by okay. So this bound is actually not hard to understand, because you look at this. The max of x1 until xn is only one of the possible, is either one of these values, x1 until xn. Whereas over here, okay, you basically have a sum, right? So over here, you basically have a sum. Okay, so definitely this sum is actually larger than the max here. Okay. So this may be maybe I'll impose a condition here. Maybe impose a condition here, non-negative, right? Easier. Okay, because if we can take negative numbers, then it may be not clear, yeah. Okay, maybe not clear which is larger. But if these are all positive terms, these are all non-negative terms, then very clear that your sum is definitely larger than the max. Okay. All right, and because you have this hypothesis, so this will be so this is equal to E of E t x1 wait just a minute, yeah. Okay, sorry, no. Okay, I made the wrong comparison. Okay, I should not compare to this part. I should compare to this part. Okay, compare to this part. Right. Okay, it's the same here. This is definitely less than the following. All right, because when you take E of max of this, it's either one of them, right? So maybe it's just maybe let's say is in this case is this guy that is the max, right? So you basically you're only taking expectation of one term here, right? And this is definitely less than or equals to taking the sum of the expectations. Okay, so this is the idea here, right? From how you generate a further inequality. And then this will be less than or equals to, by hypothesis, you will have n terms, right? E of t square sigma square over 2. Okay, so this is by hypothesis. All right, okay, so you have a sequence of arguments starting from this result. You apply Jensen's inequality, and then you use this hypothesis here to get some bound. Okay. All right. So once you have got this bound, you can now access this random variable by taking log on both sides. If you take log on both sides, you will get t of this. Okay, take log of that being bounded by log n plus t square sigma square over 2. Okay. And therefore, your expectation of max will be bounded by log n over t plus t sigma square over 2. Okay. So let me clear some space here. Okay. So once you have this, inequality, you're almost there. So we take t, right? We set t equals to square root of 2 log n over sigma. So then your expectation will become sigma log n over square root of 2 log n plus sigma 2 log n over sigma times sigma square over 2, right? So basically it's just substitution. So you cancel this. In this part you get sigma square root of log n over square root of 2 plus sigma square root of log n over square root of 2. So you add both of them, you get twice of sigma square root of log n over square root of 2, which is sigma square root of 2 log n. Okay. All right. So this is how you can actually use all these inequalities that you have learned to generate bounds for expectations. all right, of random variables. So this is an example to generate expectations for maximum of NIID random variables. Okay. So for example, if you have some, let's say for example, you have a chi-square random variable, right? So the chi-square is a non-negative random variable. So you will know that if you take NIID chi-square random variables, and you are interested in the max, right? So the mean of this max of these chi-square random variables cannot go outside of this value. Okay, can't go outside of sigma over 2 log n, where sigma is the variance, sigma square is the variance. Okay, right? So okay, so this is just the last example cover. So are there any questions with this section? Any questions for this section? Okay, so let's move on to the two results that I'm going to talk about for today. So these are two important results. First thing, maybe I will define some quantities, right? So previously, I think in one of the tutorials, you look at these quantities. Okay, you look at these quantities, right? We showed that these quantities are actually sets. They are sets in the sigma field. Okay, if your A1, A2, and AN and so on are in sigma field, then this set is also in the sigma field, and also same with this. Okay, so both sets are in the sigma field, and therefore these sets can be assigned a probability. Yeah, this set actually has a name. Okay, this set is actually called the lim sup of AN, and this is called the lim inf of AN. Okay, the lim sup AN is defined as this set. Lim inf of AN is defined as this set. And since these two sets, they are in the sigma field, therefore we can actually ask about these probabilities. Okay. And we can ask about this probability. Okay. This lim sup is actually what we call AN occurs infinitely often. And this one is like AN occurs only a finite number of times. Okay, and these two sets, based on these operations, you can generate so these two sets. Although sometimes, depending on what is your your sets A here, these sets may be easy or not easy to understand. All right. I mean, if at least if you want some kind of exact enumeration of it, sometimes whether you can write it down will depend on what is your AK. Right. But anyway, at this moment, we just look at them as a set, right? A set that belongs in the sigma field, so we can ask questions like this. Okay. All right, so we can assign probabilities to it. Okay. So the first result here is the so-called Borel-Cantelli lemma. The first Borel-Cantelli lemma. There are actually two results, first and the second, right? Borel-Cantelli lemma. Okay, so the theorem goes like this. You have A1, A2, and so on, right, in F. Okay. So if the sum of the individual probabilities of the sets, right, is finite. Okay, convergent, right? The sum is convergent. Then the probability of lim sup is 0. Okay, it's a very, very simple statement. If you check this condition and it is convergent, then this probability is equal to 0. All right, so this looks like very strange, right? How can this result be so simple? So here's the proof. Okay, the first thing is to note the following. Your lim sup an is equal to this, by definition, right? It's equal to this set. And this set is basically a subset of so this will be a subset of okay. All right. Because you see this set lim sup, right? You have a further operation here, taking intersection. Surely this set, right? After you take intersection of all these AK, it is smaller than this set without taking intersection, right? Because once you take intersection, so it could be actually equal. So maybe I'll just write as this one. Okay. Right. So after you take intersection, it cannot be larger than the origin, this set, right? It can be smaller, or at most it's equal, right? Okay. So since this set is less than that set, therefore my P lim sup of an is less than or equals to P of this set, right? Okay. And of course your P of lim sup is definitely larger than or equals to 0. Okay. Right. So this is easy. And from here we can apply an inequality. So what inequality can we apply here? Remember the inclusion exclusion formula. So this one, if you take union of this, right? This will be less than or equals to what? Anyone wants to offer a suggestion here? The probability of a union of a set of events is bounded by what? Anyone? If you look at the case of two sets, right? So this will be, okay, inclusion, exclusion result. This is bounded by what? Anyone? Nobody wants to answer this. Come on, someone.
Is it 1?
Sorry?
1.
Of course it's bounded by 1. Yeah, sure. Sure it's bounded by 1, but that's a trivial bound, right? It's also bounded by 2 or 3. So those bounds are trivial. Yeah, so basically it's just bounded by these two guys because, yeah, the sum, yeah, because your PAUB has got it subtracts a certain amount away, right? So it cannot be greater than or equals to the two sums here. So by induction, right? So this one is equal to, is bounded by P of A K, right? Right. So here you have this result, yeah. This is called Bonferroni's inequality. Okay, this is a very basic inequality for very basic inequality that appears when you try to bound the probability of a union of some events. Yeah. Okay. So please remember this, and it's actually very easy to understand also. Okay. So this result is basically by proof by induction, right? But you can easily understand it from the case of just two events. Okay. All right. So once you have got that, then this is where it comes in, right? So you see that this is a sum, right? This is what we call a tail sum, right? The tail sum of P of AK, because you are starting from K equals to N, right? N is some number, right? Can be 10, can be 100, whatever, right? The point is that this is adding towards the tail. So it's basically like if you have a bunch of probabilities like these, right? You're adding the tails here, okay? You're adding the tails, okay? Now, this is where your hypothesis comes in. Your hypothesis says if your sum is convergent, all right? So if this sum is convergent, right, what will happen to the tail sum? If this sequence of probabilities, right, you add them up, they converge to some number, fine, some number. What does it say about the tail sum? the tails. What would happen to the tail sum? What would it converge to? For example, so these are all the probabilities, right? The height. So you add up all of them. Okay, you add up all of this, you add up all of them, and they converge, equals to some number, right? What does this tell you about the tail sum? Converges to what? Converges to what when your n tends to infinity, yeah? When your n tends to infinity, what will this, when your n tends to infinity, what should this converge to?
0.
Yeah, sure. It has to converge to 0, right? Because you're adding towards infinity. If the tail does not converge to 0, right, then you basically your series, right, doesn't converge. Okay, the series converges because its tail is converging to 0. What value you get actually is determined by what you have got at the beginning. Okay, not the tail. The tail, it has to drop to 0. The sum of the tail events, right? It has to drop to 0. Otherwise, it cannot converge. Yeah. Even if it drops to some very small constant, you add them up, it still will blow up. Right? It has to sum to 0. Yeah. So by hypothesis, right? If by hypothesis this converges, this implies that this will converge to 0. Right? The tail sum has to converge to 0. So you can see that your P of lim sub an, right? The lower bound is 0, so it cannot go down already. And its upper bound, right? It's shrinking towards 0. Okay? So this implies that it will converge to, sorry, it's not even converging to 0. So it is equal to 0. Right? Because as you take limit, right? So this converges to 0, right? So it's being squeezed, right? It's being squeezed between 0 and some value that is fast approaching 0. So it becomes 0, yeah? Okay, so that's the argument, yeah? So if it's convergent, then definitely your P lim sub is equal to 0. So this is one important result, right? So later we will see how to use this result to prove some important theorems. Okay. So first, Borel-Cantelli lemma, very simple. If you have a set of events in the sigma field, and the sum of this, the probability of these events is convergent, then P lim sub is equal to 0. Okay. Okay, then we have the last thing today, the second Borel-Cantelli lemma. Okay, it goes like this. Of course, again, you always have to have this, right? If an is a sequence of independent events. So you got independence, yeah? And in this time, your sum of the Pn diverges, meaning they sum to infinity, right? Then the reverse occurs. Then P of lim sup is equal to 1. Okay. So I'm just going to go through the proof. So because the proof illustrates some important ideas, right? Okay. So what are we going to prove? So we want to prove this result, that if these conditions are true, then I want to prove this. Okay. Just a minute, yeah. All right, okay. So it turns out that in this case, right, trying to prove this is actually a little bit tricky. All right. So we will equivalently we prove. So we show that P of lim sup, the complement, right? We show that the complement is equal to 0. Okay? This is a common strategy in probability work, right? Sometimes the probability of the event that we want to show may be hard to do, right? But its complement may be relatively simple. So we do the complement. Okay, we just show equivalently the complement is true, right? So in this case, trying to show that this is equal to 1 is the same as trying to show that the lim sup of an's complement is equal to 0. Okay, and this is equivalent to showing that P of the following is equal to 0, right? Now, I claim that this thing here is equal to this lim sup. Okay, so let's see. So your lim sup an complement is same as so by definition is intersection of the unions okay, you take complement, right? When you take complement, you apply De Morgan's law, right? I think we covered De Morgan's law. So if you apply De Morgan's law, the intersection here will become the union, right? Okay, and then you have a union UK. So the C comes in here. All right. So, okay. So this is De Morgan's law, right? And then this becomes union of. So this one you apply again the complement of the union, it becomes intersection, and the C goes in. All right. So therefore, this is equivalent, yeah. The lim sup of the complement is equal to these things. So showing that P of lim sup an complement is 0 is equivalent to showing this result. Okay. So this part here illustrates a common proof strategy, which is you should, sometimes if you want to go direct, difficult, translate the original problem into equivalent statements. And in this case, your equivalent statements involve the use of a complementation, okay? All right, so basically you want to prove that this is equal to 0, all right? Now, again, you use something that you are familiar with, right? So you look at this probability here. It has a union and you treat this as one object, right? So definitely you will be able to say the following. This is definitely bounded from below by 0, yeah? Okay. Now how about the upper bound? What is the upper bound? So you treat this as one object, right? As one set. Then you will be able to see very clearly what is this bound. Anybody? You apply the result that we learned just now. Anybody? We just learned this just now.
Union of AK complement.
Sorry?
Union of AK complement.
Union of AK complement. This is a probability measure.
The probability of union of AK complement.
Okay, and then what is that further? Let's say if, well, you just treat, okay, you just think of this as, let's say if this is something like, let's say Bn, right? Let's say suppose you just think of this whole thing as a Bn, okay. What is this bounded by?
Summation of Bn.
Summation of Bn?
The summation of Bn.
Okay, summation of the probability of Bn, right? This basically just your Bonferroni, right? Again, Bonferroni inequality. Okay. All right, great. So your Bn is basically just this whole thing, right? The intersection. Don't get scared by these set operations, right? They just produce another set, right? So you can think of the whole thing as just another set, right? Don't get scared by all these notations. Okay, I know a lot of people when they see these notations, they kind of like their mind just go blank, you know. It's not necessary. It basically is just saying you take this set operation multiple times, right? Countably many times. Okay, fine. So it's some process, but at the end, it still produces a set, right? And that's it. So you think of it as a set, then things become very clear like this. You can write something clear like this, okay? All right. Now, okay, that's great. Okay, so from here, right, you want to show. So since your goal is to show that this thing here, right, it's, oops. Since your goal is to show that this thing is equal to 0, and you know that this is bounded by 0, this is bounded by the sum of this thing, right? So what should we show? Equivalently, we show what? To show that this is equal to 0, what do we show here?
Show the summation of probability of Bn is equal to 0.
Yeah, that's right. That's right. So you get the idea now, right? Now you see the way you construct the logical argument is to break it down to smaller pieces where the things that you want to show is equivalent to the smaller pieces. Okay, and then there's a link of arguments, yeah. So you complete that link, but every time you're just breaking it down to smaller and smaller pieces of equivalent statements, and then that makes the problem simple, yeah. This is the strategy to work out problems that appear to be difficult at the beginning. All right. So if you have this way of thinking, a lot of problems that look difficult can be solved. Okay, they just look difficult because you don't know how to turn it into equivalent statements, and you don't know how to join the equivalent statements together. Okay, now once you have this idea, then hopefully next time you can activate this idea. Yeah, it helps a lot in learning a lot of these abstract things. Okay, a lot of these abstract things, the argument is based on this kind of approach. Okay. So that's why it's worthwhile showing you this. Okay, so equivalently, after we establish this equivalence, we basically just need to show that P of PBN, right? So Bn, I'll just write it back like this. Just show that this is equal to 0, right? We just need to show this. Okay. Right. Now, further, how else can we simplify this statement? This statement can further be simplified. Show this, then equivalently, this is showing what? Anybody? Sum of these probabilities equal to 0 implies what? You add up all of them, they're equal to 0. What does that imply? It's very obvious. Anyone? You are summing many probabilities, right? P, you take intersection, start from the first one, then you take intersection, start from the second one, and so on, right? You add everything and it becomes 0. What does this tell you about the individual probabilities?
The individual probability is also 0.
Yeah, that's right. Only one thing can happen. If they all add up to 0, it means that all of them must be 0, right? Because they cannot be negative. Yeah? If they can take negative, then of course, then nothing much can be said, right? There are all sorts of combinations. But they must be non-negative. So when they add up to 0, there's only one possibility. All of them are 0, right? No other possibilities. At the moment one of them is non-zero, then it can't add up to 0, right? So therefore, this statement further simplifies to show that P of this thing is equal to 0. Okay? Now, you can see how far you have come from this thing that you need to prove. It ends up going through this chain of reasoning that in order to prove this result, you simply need to establish this result, which is a much simpler result to establish. Yeah? Okay, so you have already made quite a lot of progress by going up to this point. Okay, this is this part here now is will be we will see how to show this result. Okay, so let me clear the board a bit. Okay, now P of this is equal to the product of the individual probabilities by hypothesis, right? Yeah, note your hypothesis here. Your your AN is a sequence of independent events, yeah. So that's why from here, the probability of the joint is the product of the individual probabilities, right? This is by hypothesis, okay? Your hypothesis simplified it, and this one is equal to 1 minus P of AK, right? Okay, because of complementation, right? So you can write like this. Now, this part here, you have to know an inequality to make progress. So essentially, you come to this inequality because there is an equality and inequality that says so. So this is one of the important inequalities. The other inequality is concerning exponential. Okay. So this one you can show very easily because you're by infinite series, right? So because your left hand side is equal to 1 plus x squared over 2 plus until many things, right? And this is your so-called Maclaurin series, right? Maclaurin series. So definitely this is larger than 1 plus x, okay? So in this case here, your x is greater than 0, yeah? Okay. So here also your x is greater than or equals to 0. Okay, but this inequality here is obtained in a slightly different way. Okay, because there's a negative here. So it seems like you can replace the x with minus x and then still get the same thing. If you want a more rigorous demonstration of this result, it goes like this. Okay, so this part here, we know the following. The log of 1 minus x is equal to minus x plus x squared over 2 plus x cubed over 3 and so on. This is the infinite series representation for log of 1 minus x, right? You can actually get this from calculus. All right. So this is basically you can generate this as follows using integration. So you take integral of minus 1 over 1 minus x dx is same as log of 1 minus x, right? Plus c. Okay, of course here here my x is between 0 and 1. Okay, my x is between 0 and 1. Okay, it can take 0, right? So this one, this integral is equal to log of that, right? Because you take the derivative, so the first part, the numerator is the derivative, the denominator is here, right? So then, but then this integral, right? The left-hand side is equal to integral of the minus sign take out. So if we integrate 1 over 1 minus x, that's 1. So 1 over 1 minus x is a geometric, is the convergent, is the value for 1 plus x squared plus x cubed and so on, right? The geometric series, okay? So you integrate this geometric series one by one, all right? You will end up with x plus x squared over 2 plus x cubed over 3 and so on. Okay, so your negative sign is outside, right? Negative of everything. Okay, plus c. Okay, so you can determine that c is 0 because when you plug x equals to 0, both sides are equal to 0, right? So your c is 0. That's how you get this inequality. Sorry, this series. Okay, so once you have got this series, then what happens? So you can do the following. So your log of 1 minus x is equal to minus x squared over 2 minus x cubed over 3 and minus everything, right? Therefore, it's less than or equals to minus x, right? Because it's got a whole bunch of negatives added to it. Okay, so it's definitely less than or equals to minus x. Yeah. Okay, at most it's equal to minus x. So you get this inequality, right? Log of 1 minus x less than or equals to that. Take exponential on both sides. You will get this inequality, right? Which is basically this thing. Okay, so these inequalities are obtained from infinite series. If you know your infinite series well, you can basically construct these inequalities on your own, yeah? Okay, so anyway, so this is the result that you have to use here, right? So your exponential of minus x has this. So if you replace the x with p of ak, this will become p of ak, okay? Because your p of ak basically is some value between 0 and 1, right? So it fulfills all these conditions, okay? So this is very crucial, right? This step is very crucial because otherwise you will get stuck here, right? You don't know how to continue, but you know that it is bounded, yeah? Bounded by this thing, and this thing is equal to E of minus sum of P A K, right? K equals to N until infinity, right? Now this is where your second hypothesis comes in useful. Your second hypothesis, so the first hypothesis is here, independence. This is a second hypothesis. The sum is divergent. So when the sum is divergent, what will happen? Look at here. Okay? When the sum is divergent, what will this become? Okay, in fact, it's just equal to 1. So when this is divergent, it becomes infinity. E of minus infinity, it will become what?
0.
0, right? By hypothesis, right? Okay? So you end up, so you end up having your P of, so this thing, right? We now know that it is bounded between 0 and 0, which can only mean one thing. It implies that your PNAKC is equal to 0, right? Because it's being squeezed between these two values, lower value and upper value, squeezed between these two values, but these two values are the same, which basically implies that it is at that particular value, okay? So then you complete your proof, yeah? That this result is true, okay? So it's quite a long chain of argument, but you can see that in every step, things become simpler. And right to the end, over here, our goal is to show that it is equal to 0. So over here, the idea is to find some bound. Because you cannot evaluate this because you don't have information to evaluate it, right? But you could use some bound, and then you can combine it with the hypothesis to lead to this result, okay? So this completes the proof for the second Borel-Cantelli lemma. So the proof is shown here because it is very instructive in terms of teaching you how to think about reading this kind, constructing this kind of arguments, yeah. Okay. Are there any questions from you regarding this second lemma? Okay, so okay, you might want to watch the video again just to follow it more closely if you were not able to follow it just now. All right. Okay, so now I want to just let's say look at the tutorial a bit. Okay, let's go to spectrum. Okay, so can you see tutorial 5?
Yes.
Can you see tutorial 5?
Yes, can see.
Okay. Okay, so I think we don't have time to go through this today. So I will just ask students to prepare for this for next week. Yeah. So any volunteers you want to do? There are 5 questions here. Anybody wants to volunteer for the questions?
Doctor, I look question 1.
Okay. Kareem, right? Kareem, question 1. Okay. Problem 2. Anyone? Problem 2. Okay, sorry. I think okay. Just now, I think the connection dropped off. So okay. So now I think it's back again. Right. Question 2. Any volunteers? Okay. Nobody wants to do question 2. If you do this
Okay,
kind of
I think I
questions,
can do.
your understanding will improve. You know, it will help a lot when you
I think I can question 2.
when you go for exams. Yeah. Eugene. Okay. So let's look at the problem 3. Chang, where is Chang? Chang here? Chang, are you here? Okay, Chiu Jiasheng here.
Yeah, doctor, I'm here.
Okay, you want to do 3?
Maybe I will try lah.
Yeah, try 3.
Okay, no problem.
Okay, number 4. Just showing those bounds for a particular example. Is Amirul here? Amirul Zawawi? Okay. How about Parvan? Parvan, are you here? Parvan? Okay, you try number 4, yeah? Then the last one is just this one is just basically some verification, just verifying some results for the geometric. If your x is a geometric random variable, so this should be quite straightforward. Is Fadila here? Fadila Sulaiman. Okay, not here. Atira Nudra.
Yeah,
Atira.
doctor.
Can you do 5?
Okay, doctor.
Okay. Okay, so that's all for this part. Okay. Okay. So I think that's all the time we have for today, right? So that's all for today. Thank you.
Thank you, doctor.
Stop the recording now, yeah.